Yes, so welcome. So we'll continue where we left off in the previous video. So in the previous video we started ideals, right? So in the previous video, so we'll just recall what we saw in the last class. So first we have defined what's meant by ideal. So for ideal, first we have defined left ideal and then we have defined right ideal. So for left ideal, first that subset has to be a subgroup with respect to addition, and R into S belongs to S for every R in R and every S in S. And right ideal means the same condition, first condition is same, the first it has to be subgroup under addition, and S R belongs to S for every S in S and for every R in R. So after seeing left ideal and right ideal, we have seen what's meant by ideal, right? So a subset is said to be ideal if it is left ideal as well as it is right ideal. And then you have seen the intersection of two left ideals again left ideal, and intersection of two right ideals also again right ideal, and arbitrary intersection of left ideals again left ideal, that we have seen. And then you have seen some examples that the set of all 2 cross 2 matrices of the form A0 B0 is a left ideal but it is not right ideal. And second example is a set of all the fixed integers is a two-sided ideal, and the set of integers is only a subring but not an ideal of the ring of rational numbers that we have seen in the previous class. And the set Q of rational numbers is only a subring but not ideal of a ring of real numbers. And then we have seen some examples that the set of all diagonal matrices is neither right ideal nor left ideal, that we have seen. And then we have seen that intersection of two ideals again ideal, and that's it, right? Yes. Now we will be proving some theorems based on ideals, right? So more about ideals. So first we are going to start with, there are 4 to 5 theorems. I will be solving three theorems and 2 will be left as exercise, very easy proofs. So first we will start with the first theorem on ideals. So the theorem 1. So theorem 1 is, a field has no proper ideal, right? A field has no proper ideal. A field has no proper ideals, right? That is, the only ideals of the field are 0 and F itself. That is, only ideals are 0 and F itself, right? So these the only ideals are 0 and F itself. So we will prove this. So we know what's meant by field, right? So if non-zero element has a multiplicative inverse, and with respect to addition and with respect to multiplication it has to be an abelian group. So we will prove this. That is, we need to prove that only ideals, that is, there is no subset which will be ideal, there is no proper subset for a field which will be ideal. So a field has no proper ideal. So let S be any non-zero ideal of a field R, and let A be any zero element of S. So let S be non-zero ideal of F, right? So F is a subfield, F is a field, and I am taking a subset S, right? So I am taking an S to be a non-zero ideal of F. Now let us take an element A. Let us take an element A in S, right? So I am taking a non-zero element A. Now can I say A inverse belongs to F and this A is not equal to 0? Because by definition of field, so when I say field, it has multiplicative inverse. So therefore A inverse will be belongs to F. A inverse will be in F, right? So since S is ideal, so S is ideal means it is left ideal as well as right ideal. So that means this S has to be a subgroup under addition. And if you take an element S in capital S and if you take an element small r in capital R, then this element will be in S by definition of ideal. So I am taking an element A in S and A inverse in F. Can I say A into A inverse will be in S? Right? Can I say A into A inverse will be in S? So this implies, so we have A belongs to S, A inverse belongs to F. So by definition I can write A into A inverse belongs to that. So by definition of ideal. So I'm using left ideal here, right? So A into A inverse will be in S. So A into A inverse means 1. So 1 belongs to S. 1 belongs to S, right? So let X be any element of F. Now you can see this I 1 belongs to S. 1 belongs to S. Now let us take now let X be any element of F. Any element of F. Now I am taking X to be any element of F. Now since 1 belongs to S, so what can you conclude about X into 1? X is in F, 1 belongs to F. So this implies X into 1 belongs to S for all X. For all X. Now if I vary all X, I will get this S to be equal to F, because we will get the entire set, right? Because we are multiplying X into 1 belongs to S, and this X belongs to this X, for every X belongs to F. So we will get every element in F is in S. That means this is equal to F. So I have taken S to be a non-zero ideal. I have taken S to be equal to F. So we have S is equal to F. So S is equal to F, right? So therefore the only ideals are 0 and F itself. So I think it's a first we are saying that 1 belongs to S, and after saying 1 belongs to S, we are using the definition of left ideal to show that if you take an element X in F, and since 1 belongs to F, X into 1 will be in S, and since X belongs to field F, so this S has to be equal to F, because every element in X belongs to every element of X. So every element of X is also in S. That means F has to be equal to S. So the only proper ideals for a field are 0 and F itself. Now the second theorem. Now the two theorems. Now next we will move on to the next topic, which is proper ideal. So a commutative ring with unity is a field if it has no proper ideal. Okay, we will prove this. A commutative ring with unity is a field if it has no proper ideal. If it has no proper ideal. So a commutative ring will be field. Commutative ring means a commutative ring with unity is a field if it has no proper ideal. So a commutative ring means first it has to be an associative ring. So associative ring plus associative ring, and with respect to multiplication it has identity, and it is commutative also. That is A into B is equal to B into A. Suppose if we have an extra condition that the non-zero element has inverse, then it will be a field. Suppose if you want to neglect that condition, suppose if you want to have an alternate condition for a non-zero element should have inverse, this is equivalent. A commutative ring with unity is a field if it has no proper ideals. So a commutative ring with no proper ideal will be a field, right? So for field we will show, after these three conditions we will show that non-zero element will have an inverse. So instead of showing this, we can also show that if it has no proper ideals, then it will be a field. Right? A commutative ring with unity is a field if it has no proper ideals. So we will prove this now. So let R be a commutative ring with unity having no proper ideal. So I am assuming that R is a complex ring with unity, it has no proper ideal. I'm going to prove that it is a field, right? Yes. So prove. So let R be a commutative ring with unity with no proper ideal. With no proper ideal. So what I need to prove? I need to prove that this R is a field, right? R is a field. So a commutative ring with unity with no proper ideal, I'm assuming that I need to prove that it is a field, right? So we already showed in the previous theorem that R will be a field has no proper ideals. That is, we will show that only ideals are 0 and f itself. So we need to prove this condition. Just now we have proved the previous theorem that a field has no proper ideals. That means the only ideals are 0 and f itself. So we will prove this. Now we need to prove that it is a field, right? So R is a field, only ideals are 0 and f itself. Actually we need to, we will assume that it has no proper ideal, right? So we will prove that it is a field. So I will give you alternate proof. So let R be a commutative with unity, that is only ideals are 0 and R itself, right? So what we need to prove? It is a field, right? It is a field. That means we should show non-zero element possesses a multiplicative inverse. Non-zero element possesses a multiplicative inverse. So I need to prove that it's a field. I'm assuming that it's a commutative with unity with no proper ideal. So that means with no proper ideal means the only ideals are 0 and R itself. I need to show that the non-zero element possesses multiplicative inverse, right? Yes. Now let us take an element A in R. Then the set RA, right? The set RA, it is the set RA such that this R belongs to R is an ideal of R. Right? So surely you can you can refer the previous theorem for the proof, but it's a we already proved this kind of we need to prove it's an ideal. That means you just show that this is an it's a subgroup with respect to addition. So for showing the subgroup, it is enough to show that it is we need to show that it's a subgroup, right? So you just need to show AB inverse belongs to H, sorry, AB inverse belongs to RA. I mean to show left ideal as well as it is right ideal. So this set will be a ideal, right? So very easy task to prove that this set is an ideal. So therefore this is an ideal of R. I am taking element A in R. We already know that the set of all fixed integer is always a ideal, right? So again here RA is a fixed integer, right? But here R belongs to R is any commutative integer. We already proved one example. The set of all fixed integer is a ideal, and there we are varying. I am fixing A and varying integers, but here I am varying R to be any commutative ring, right? So let the set RA is an ideal of R. Now since 1 belongs to R, why? Because it is a commutative ring with unity. It has a unit element, that is it has 1. So since 1 belongs to R, because R is commutative ring with unity, right? So it has a number 1 in R. Now therefore what about 1 into A? 1 into A will be in R. 1 into A will be in 1 into A is equal to A, and this will be in RA, and this will be in ideal, because here we are having commutative ring, and here I am taking an ideal R into A. So by definition of ideal, if I take an element from here, if I take one element from here, then it is left ideal as well as right ideal. So multiplication of these two elements will be in RA, and multiplication of these two elements will be in RA. So I am taking an element A in R and 1 in R, right? So therefore we can conclude that 1 into A which will be RA. So therefore A belongs to RA. Therefore, the ideal RA is not equal to 0. Since R has no property, therefore only possible RA is equal to R. So we have produced one element A in R, and I am varying A to be in R. That means this RA has to be equal to whole R. This RA has to be equal to whole R. Thus, every element of R is a multiple of A by some element of R. Right? So every element that means RA is equal to R. That means every element of R is a multiple of some element of R. Every element of R is a multiple of some element of R. In particular, if one belongs to R, so it can be realized as a multiple of A. Therefore, there is a B such that okay. So every element of R is a multiple of some A into R, right? So if one belongs to R, then 1 is a multiple of some element, right? 1 is a multiple of some element. So therefore this 1 can be written as some B into A, because every element is a multiple of. So therefore 1 is equal to B into A means therefore A inverse is equal to B. Therefore it possesses multiplicative inverse. We need to show that non-zero element has multiplicative inverse. Therefore we have proved A inverse, that is the B is a inverse for A, right? So therefore R is a field. So similarly, what you can show is, you can also show that let R be a ring with unit element. R not necessarily commutative. Show that only right areals are 0 and R. Prove that R is a division ring. So you just take theorem 4 exercise. So this is a right areal. You can easily show. We already proved this. So you just take this exercise, theorem 4. It is in page number 317. That let R be a ring with unit element. R not necessarily commutative. Show that the only right ideals of R are 0 and R, then prove that R is a division ring, right? Yes. So now we'll move on to principal ideal, right? Principal ideal. So far we have seen ideals, we have seen some theorems, and then we have seen some examples. Now we will be moving on to principal ideal, right? So it is more or less similar to cyclic groups. So now we will discuss principal ideals. So principal ideal. So first we will define principal ideal. An ideal S of a ring R is said to be a principal ideal. An ideal, of course it has to be ideal, then only we can talk about principal ideal. An ideal S of a ring R is said to be a principal ideal. Is said to be a principal ideal if there exists an element A in S such that any ideal T of R, any ideal T of R containing A also contains S. That is S is equal to, that is, if an ideal can be generated by a single element, we call that as principal ideal, right? So very simple, don't worry about the definition. If an ideal can be generated by a single element, then we can say that ideal is principal ideal, right? In cyclic group, what we will do is, if we can generate the entire set with a single element, we call that a cyclic group. So if we can generate an ideal with a single element, then the ideal is called principal ideal, right? So an ideal generated by a single element is called a principal ideal. a principal ideal, right? So first you verify that it is an ideal. So for ideal, that S has to be a subgroup with respect to addition, and it has to be two-sided ideal, that is AR and SR and RS both should be in S for every R in R and every S in S. So if that set can be generated by a single element, then the ideal will be called as a principal ideal. So if a ring R has unit element, then an ideal generated by 1 is the whole ring 1 is equal to R. So we will discuss some they have briefly discussed one paragraph. If a ring R has a unit element 1, suppose a ring R has unit element 1, then an ideal generated by 1 is the whole ring, right? Because the ideal generated by 1 is the whole ring, right? Since every element R in R will be written as R into 1, right? Because we can see, suppose if a ring R has unity, suppose if our ring R as 1, that is if there is an element 1 in R, then every element in R can be written as generated by 1, because 1 into R is nothing but 1 into R, and this R belongs to R. So I can generate this entire set with a single element. Therefore a ring with unit element will always, that entire set will be a principal ideal, right? So for this reason, ring itself is called a unit ideal. The ring itself a unit ideal. Suppose if a ring R has 1 in it, then that ring is called, that is actually it will be improper, it is called a unit ideal. The ideal generated by 0 consists of the 0 element alone is called null ideal, right? So the ideal generated by 0 is called null ideal. So every ring R has at least one principal ideal, namely 0. Every ring R, because if I say ring 0 should be in R. So if I can generate that entity set with 0, we will have only one element 0. So every ring R has at least one principal ideal, namely 0. Every ring with unity has at least two principal ideal, which is 0 and 1. That is an ideal generated by 0 and ideal generated by 1, right? So a ring will always have a null ideal, that is an ideal generated by 0, that is this set has only an element 0 in it. And suppose if a ring R with 1, that is it has a unit element, then it will always have two ideal. One is generated by 0, which is null ideal, and generated by 1, which is the entire ring. So this is called an unit ideal, that is the set generated by 1, which will be a whole ring, is called unit ideal and is called null ideal. So ring always have one principal ideal, and a ring with unity will always have two principal ideal. There can also be some other also, but surely we will have two principal ideal, and a normal ring has one principal ideal, right? Because these two are basic results, that every ring R has at least one principal ideal, namely 0. Every ring with unity has at least two principal ideal, which is an ideal generated by 0 and ideal generated by 1, right? Yes. So now I'll just quote one theorem, and I'm not going to prove this theorem. I'll just quote one theorem, and then you will see some examples. I think you can if you understand the definition, you can easily follow all the theorems. So first theorem is, I'm not going to prove this theorem. So if A is an element, if A is any element in a commutative ring, any element in a commutative ring R with unity, then the set S R into A, and this R belongs to R, is a principal ideal, principal ideal generated by A. Again, it's a very natural result. So if you just take an element of the commutative ring R, then you just form the multiples of A, then the set will be a principal ideal generated by A, right? Natural this theorem. So you can easily prove this. Now suppose, for example, let us take I give an example. Let us take the commutative ring R to be integers. This is a commutative ring with unity because it has 1 in it, and also it is a commutative ring. Suppose if I want, now whatever element you take, now suppose if I take an element 5 in R, if A is any element of commutative ring R, then what is the set generated? What is the set generated by 5? So we can generate S is equal to divided by 5, which is 5R, and this R belongs to R. This set is nothing but 0 plus or minus 5 plus or minus 10 plus or minus 15, etc. And this will be a principal ideal because we can generate the entire set with 5, and also it is an ideal. It is a for ideal we need to show that first it has to be subgroup with respect to addition, and it has to be SR and RS should be in S. Surely it will be in S, right? Because R are multiples of 5. So therefore, whatever element you take, that element will be a principal ideal. So for important conclusion is whatever element you take in R, then that ideal will be principal ideal. So for every A in R, the set generated by A is a principal ideal. That means we can have an infinite number of principal ideal in this commutative ring. Whatever element you take, if you want take A to be equal to 1 crore, the set generated by 1 crore is again a principal ideal. So whatever element you can take, the set this set will be a principal ideal. So there are infinitely many principal ideals in the set of integers with respect to addition. Now we will define what's meant by principal ideal ring, right? Now we will define. So first we have defined what's the principal ideal. Now we will define what is meant by principal ideal ring, right? So far we have defined principal ideal. Principal ideal means first it has to be ideal, and we can generate that set S with a single element. Now we will define principal ideal ring. Principal ideal ring, right? So principal ideal ring, a commutative ring R without zero divisors. Okay. So if every ideal is of the form, if every ideal is generated by element A, then the ring is called principal ideal, right? So if you just collect all the ideals and you just verify every ideal can be written as can be generated by a single element, then that ring is called principal ideal ring, right? That is, every ideal is a principal ideal. Every ideal is a principal ideal means it is a principal ideal ring. That is, every ideal is a principal ideal. Every ideal is a principal ideal. So let R, a commutative ring R without zero divisors and with unity, is a principal ideal if every ideal is a principal ideal. So we will define correctly. So a commutative ring R without zero divisors, right? It has to be without zero divisors. If it is with zero divisors, we cannot talk about principal ideal ring. So to qualify for principal ideal ring, first it has to be a commutative ring without zero divisors and with unity. That is, it should have 1, and with unity is a principal ideal ring. So IPAR It's a principal ideal ring. If every ideal yes in R, if you take whatever ideal you take yes, then that ideal will be that ideal will be principal ideal. So every ideal in S in R is a principal ideal. So whatever ideal that R has, that ideal has a principal ideal. That means whatever ideal you find, that ideal I can generate with single element. So if that happens, if every ideal is a principal ideal, that ring is called a principal ideal ring. Principal ideal ring. So just now we have proved that the set of all. Just now I have said one example that the set of all integers, every ideal is a principal ideal. Theorem 1. Theorem 1. The ring of integers. The ring of integers is a principal ideal ring, PIR, right? So just now we have showed, just now we have proved, right? So every element, if you take an element A in R, the set generated by RA is a principal ideal. So whatever ideal you have for integers, then that will be a PIR, because I can generate that entire set with right. So again you can just refer proof, again this is proof. So and also every field is a principal ideal ring. Theorem 2. Every field is a principal ideal ring, right? So if it is a field, then only proper ideals are 0 and F itself. So we can generate 0 with 0, and 0 will be in PI, since it's a combinatorial ring, 0 will be there. And since 1 belongs to R, then that is the only, since the field has only proper ideals, that means 0 and actually you can write proof in your own. So just write the proof that the field has only proper ideal, which is 0 and 1. We can generate the ideal 0 with an element 0, and we can generate an ideal F. We can generate the ideal F with an element 1. So therefore we can the only proper ideals, only ideals are 0 and F itself. We can generate 0 with 0, and we can generate 1 with we can generate the entire field with 1. So therefore these two are principal ideal, and since every ideal is a principal ideal, it is a principal ideal ring. This is enough to write the proof, right? So you can write proof in your own. Now we will define what's meant by units, right? So this is the proof for this, right? So just now I have said we know that every field has only two ideals, which is 0 and F itself. We can generate 0 with an element 0, and we can generate the entire field F with 1, because 1 belongs to R, 1 belongs to field. Therefore now we will define what's meant by units, right? We will define what's meant by units. So again very easy, units. So if an element has multiplicative inverse, then the element is called units, right? An element has multiplicative inverse. So today we have defined what is meant by principal ideal, and then we have defined what's meant by principal ideal ring. So principal ideal ring means every ideal is a principal ideal, means it is a principal ideal. So a very important result is the set of integers is a principal ideal ring, and every field is a principal ideal ring. Now you will define what's meant by units. Unity is different from units. Unity means 1. Unity means 1. Units means, suppose units means, let R be a commutative with unit element. Let R be a commutative ring with unit element. With unit element. Let R be a commutative ring with unit element. An element A is called unit. An element A belongs to R is called unit if A has multiplicative inverse. That's it. If A has multiplicative inverse, right? That is if there exists B in R such that AB is equal to 1. there exists B in R such that AB is equal to 1, right. So in other words, units of R are those elements which possesses multiplicative inverse, right. So units are those elements. 0 is not units, 0 is not units because 0 does not possess multiplicative inverse. So suppose if we have a commutative ring with unity, any element other than 0 is a units, any element other than 0 is a unit, right. So if you, under multiplication, you just collect all the elements that has multiplicative inverse, then those elements are called units, right. Unity means 1, units means all those elements which has multiplicative inverse. The student should not confuse a unit with the unit element or unity element of the ring R. There may be more than one units in a ring, there may be more than one units in a ring. For example, a commutative ring with unit element, every element other than 0 are units, right. There are infinite many units, but there is only one unit. There may be more than one units in a ring, but the unity element is always unique. Unity means multiplicative identity with respect to multiplication, right. So of course unity elements is also one of the units, right. Unity elements also one of the unity means only one unique multiplicative inverse. Units means if set of all those which has multiplicative inverse. Surely unity is also units because one also has multiplicative inverse, right. Yes. So if every non-zero element of a field possesses multiplicative inverse, therefore yes, okay. So we will now find all the units of important problem. Find all the units of the integral domain of Gaussian integers, right. We need to find all the units of Gaussian integers, that is we need to find all those elements which has multiplicative inverse. We need to find all those elements which has multiplicative inverse, right. So you just collect all the elements which has multiplicative inverse, then form a set, then the set then that are called units, right. Unity means multiplicative identity which is unique. So a very important problem, find all the units of the integral domain of Gaussian integers. Problem, very important problem. Find all the units. Remember, we need to find units, right. Units means we can have more than one. Find all the units of the integral domain. Find all the units of the integral domain of Gaussian integers. We already defined what's meant by Gaussian integers, right. We need to find all the units of Gaussian integers. So this is recall what's meant by Gaussian integers. The set D is of the form a plus bi, and this AB belongs to Z. This set is called Gaussian integers, that is a set of all complex numbers if AB belongs to integer, right. AB belongs to integer. Surely this will be subset of the complex numbers, and this is we need to find all the units for this set, or we will write set of all a plus ib. Okay. Now we need to find all the units for what we need to do. What we need to find? We need to find units of B. That is we need to find multiplicative inverse. We need to find all elements which has multiplicative inverse. We need to collect those elements which has multiplicative inverse. So we need to collect all those elements which has multiplicative inverse. right? So we need to find all those elements which has multiplicative inverse. So we know what is the unity of D. We already know unity. Unity of D is 1, right? 1 plus 0 is the unit element, because a plus bi into something, you need to get a plus bi again. So that means this number has to be 1 plus 0i. This we already discussed. So multiplicative identity for the set of all Gaussian integers is 1 plus 0i. So we need to collect all those elements x plus iy such that x plus iy into inverse, right? So we need to multiply, let us say the inverse is x dash plus iy dash, right? So usually we will write x plus I whole inverse. So just for the notation, let us say the inverse of x plus iy is x dash plus iy dash, and we need to get 1 plus 0 as an answer. So we are collecting all those elements x plus iy which has multiplicative inverse, that is we need to find some other x plus iy such that this into this will give you 1. So we need to collect all those x. We need to collect all those x. Okay. Now it's a simplification. So we need to find all those x and y which has multiplicative inverse. Now just multiply this x into x dash plus I into xy dash plus I into x dash y plus I square y dash is equal to 1 plus 0i. So we just equate real and imaginary part. So this is real part because I square is minus 1. So we will have x dash minus y dash. Now if I take I common, we will have xy dash plus x dash y is equal to 1 plus 0i. So we just equate real and imaginary part. So we have x into x dash minus y into y dash is equal to 1, and xy dash plus x dash y is equal to 0. So mark this as equation number 1, mark this as equation number 2. So we need to solve these two equations. We need to find the value of x and y. So yes. Now we need to solve for x and y. So you can also use elimination method to find the value of x and y. So I'll do some other methods. So what I'm going to do is I'm going to square and add 1 and 2. So squaring and adding 1 and 2. Squaring and adding 1 and 2. So you just square it and add it. So what you will have? So square every element. So we will have x dash square. We will have x square we will have x square x dash square plus y square y dash square plus x square y dash square plus y square x dash square is equal to 1. So if squaring on both sides will be whole square, this will be whole square, and if you apply a square a minus b whole square formula, so here a plus b whole square formula, so a square is x square x dash square plus b square, so y square y dash square, and here we will have minus 2ab, and this minus 2ab and plus 2ab will get cancelled. So here we will have x square y dash square x dash square y square. So squaring and adding, this will be whole square, this will be whole square, apply a minus b whole square formula, add, you will get this result. Now so this can be written as x square plus y square into x dash square plus y dash square is equal to 1. Now the product of two positive integers can be equal to 1 if and only if one of them is 1, right? So now the product of two positive integers can be equal to 1 if and only if each one of them is equal to 1. Remember here x, y, x dash, y dash all are belongs to integers because D is set of all a plus bi and ab belongs to integers. So here all are integers. So this is integer, this is integer, right? So the product of two integers they are getting 1. That means both has to be equal to 1, right? So so you can also argue that this can be 1 by 2, this can be 2, but this cannot happen because 1 by 2 is not belongs to integer. So the product of two integers is equal to 1 means every number has to be equal to 1. So since x dash, y dash belongs to integer and product of two integer is equal to 1 means both are 1. Both are 1. So therefore what we can conclude is, x square plus y square has to be equal to 1, as well as x dash square plus y dash square also has to be equal to 1, right? X dash square plus y dash square has to be equal to, we need to find x and y. So therefore x square plus y square is equal to 1, right? Therefore this implies, so what are the possibilities for x and y? So here x and y are integers. So x and y are integers. We are squaring and adding two integers, we are getting 1 as an answer, right? So case 1, x can be 0, y can be 1. X can be 0, y can be 1, right? X can be 0, y can be 1. And case 2 is y can be 1, x can be 0. These are the two possible choices. So if x is equal to 0, y is equal to 1, we will have y can be plus or minus 1, right? These are the two possible choices. So this can be 0 and this can be plus 1 or minus 1. So both the square will be equal to 1. And case 2 will be y is 0, so x can be plus or minus 1. X can be plus or minus 1. So therefore you just combine this and this. So x is 0 here and x is plus or minus 1 here. X is plus or minus 1 here. So therefore 0 plus or minus 1, and if you combine this and this, y can be 0 plus or minus 1. So therefore okay, so we will write this in so x is equal to 0, y is plus or minus 1. X is equal to 0, y is plus or minus 1. That is 0 plus 1, 0 plus I1 or 0 plus I into minus 1, because it is a Gaussian integers. So x plus iy. So x is 0, y can be 1, x is 0, y can be minus 1. So here x can be 1, x can be minus 1, right? I into 0, I into 0. So these are the 4 units for Gaussian integers. So which is I, which is minus I, this is 1 and this is minus 1. So therefore the answer is units of Gaussian integers are 1, minus 1, I and minus I. So you can also say that the units of Gaussian integers are the 4th roots of unity. Now we will do what's in by associates, right? So we will define what's in by associates. So therefore it's an important problem. This will ask the exam. Find all the units of Gaussian integers. So therefore you have to proceed like this. Very easy problem. So the answer is 1, minus 1, I and minus I. Now we will define what's meant by associates, and then you will see some illustrations, and then we will move on to, there are some definitions, greatest common divisor, relatively prime elements. Now next we will move on to polynomial rings. So after defining associates, next topic is polynomial rings. So we will define associates now. Associates, right? Associates. Let R be a commutative ring with unity. Let R be a commutative ring with unity. An element A is said to be an associate of A, then an element A of R is said to be an associate of B. An associate of B, which is in R, if this A can be written as some multiples of B. A can be some multiples of U. So A is equal to UB for some unit U in R. Right, so for some unit, that is U cannot be equal to 0, right? So you can see in the, if you take R to be a set of all integers with respect to addition dots, a commutative ring, then 2 is an associate for 6 because 2 can be written as 6 is an associate for U, right? Because 6 can be written as sum 3 into U. So here U is 2. So these two are associates. So for some units U in R, right? So and let R be commutative ring with unity. An element A is said to be an associate of B if A can be written as U into B for some unit U in R, right? For some unit U in R. So in symbols, you express A and B, which let us S or B, or A, B are associates. Okay. Okay. Now illustrations. The only units of the integral domain of integers are 1 and minus 1, right? The only units means the element which has multiplicative, if an element has multiplicative inverse, the only units of integral domain of integers are 1 and minus 1. Therefore, if A is an non-zero integer, then it has either two associates, namely A. Okay. So integral domain has only two associates, which is 1 and integral domain has only two units, which has 1 and minus 1. In any commutative ring with unity, the associates of 0 is only 0. Those are very natural results. The only units of the domain of Gaussian integers are 1, minus 1, I, minus I. Just now we have proved. Okay. Right? Yes. Now we will define polynomial rings. So polynomial rings are very important in UPSC point of view. We have to define greatest common divisor, that we will define when we are defining a unique factorization domain. So now we will, next video we will start polynomial rings, right? Actually polynomial rings very easy. It's a very easy. These are the problems that you studied in school, but we will going to prove these all. That is division algorithm, Euclidean algorithm, and then unique factorization theorem, and then we will see some remainder theorem, right? So we will see some based on polynomial rings, right? So next video we will start polynomial rings. Thank you. We will continue tomorrow. Thank you.